Welcome to week 4 in this course on big data. So in this week we will start looking at the foundational tooling that we actually require to get our work done in the world of big data. In the previous week we took a look at the types of data and the formats and how data was getting produced, and we concluded the week by looking at what were the options for OLAP. And in that context, we had spoken about briefly data lake, lake house, data warehouse, and those kinds of structures. In this week, we will start to look at what the tools are and what was the original tool that was used for building a data lake, which was Hadoop. And then we'll take a look at what was Spark and pay a lot of attention to Spark. And through the course of this entire set of weeks coming forward, we will actually use PySpark as the basis for all of our engagements. Great. So let's start with a brief overview of Hadoop first, because it's important to understand why certain technologies came about, and that context always makes the appreciation of what is currently happening a lot more grounded, right? So that you don't get carried away by the hype or by misconceptions that might be floating around. So when Hadoop came into picture, it first started off as basically a MapReduce execution engine, and the file system itself, which was the Hadoop distributed file system. So that was HDFS and that was MapReduce. So these two are the only technologies that initially were built up, along with some foundational technologies which Hadoop itself uses behind the scenes. It's not visible for the end user, but it is used behind the scenes. Over a period of time, what happened is, because of the open source nature of the project itself, being part of the Apache Software Foundation, a lot of different companies and academic institutions started contributing to the Hadoop ecosystem. And as a result, from one project being done by, being created by Yahoo, it became this really popular multi-company, people effort. Like more than company, it was the people that drove the popularity. And this has resulted in a variety of tools, a lot of it actually to do the same thing, right, in effect. But these options were created over a period of time because there were gaps in the other options that were available at that particular point in time. So as a result, Hadoop became over time a complex beast of multiple overlapping set of functionalities and tools. You could pick and choose which ones you wanted, but in that flexibility also lies the problem of too much of configuration to manage, a lot of interdependencies to worry about. For instance, I want this particular tool which does SQL really well, but I don't know for a fact that it's actually going to work with all the other libraries that I also need. So then there is this entire challenge of figuring it out, whether it actually works, doing some testing, integrations, and then midway through something's failed, or worse, there's a set of library changes that happen. Is it backwards compatible with all the other dependencies that I have? So those start becoming challenges. So what happened was, over a period of time, the Hadoop ecosystem itself called for having dedicated administrators who would be responsible for figuring this out and supporting the Hadoop platform day in, day out. The developers themselves had their own tooling, which was very specific to the skill set they had. As an example, the SQL developers would do only stuff in SQL. They wouldn't really worry about what happened in MapReduce or what happened in the Java backend. Then over a period of time, Python came about, but then Python didn't have the requisite support in terms of the first principle APIs and SDKs. It took a bit of time for that to come up. And then what happened was, multiple different investments were made in making some of the backends better and better. In the meanwhile, there were common problems which are getting solved again foundationally, and as a result, newer technologies came about, etc. So, just keep this in mind when people say Hadoop is complex. It's not because it started complex, but it actually started as an extremely flexible ecosystem, which made it very conducive for open source, very conducive for multiple different parties to collaborate and build. But that became also its bane, and that's why today, if you see, not many people actually use Hadoop in its form factor. Like, that's the reality, because it just became a very complex piece to manage. Instead, there are parts of Hadoop which have been packaged together and made available, especially on public cloud, right? That makes it easy for you to consume, easy for you to just click and deploy, and you don't have to worry about the internals if you don't care, right? If you do care, obviously you have the flexibility. All right. Yeah, actually, just as a bit of an aside, back in the day when Hadoop got spun off from Yahoo officially, it was branded as a company called as Hortonworks, and then Hortonworks is spelled as Hortonworks. Hortonworks actually came second in terms of launch to the market as a Hadoop distribution. Prior to that, there was a even more popular company, which still is a very popular company, which is called as Cloudera. Ironically, the name has the word cloud, but they actually were not native to the cloud or were ready for the cloud until recently. But Cloudera pretty much captured the market when it launched back in the day to effectively make the best use of the Hadoop popularity that is growing in the tech ecosystem. And then there was a third distribution called as MapR, which was specifically designed to make the entire execution environment at the foundational level super fast, like much faster than open source Hadoop. But MapR was proprietary, so over a period of time, its takers become lesser, and it got bought out by that company. And then after a point of time, Hortonworks also got merged into Cloudera. So today, if you see from the open source ecosystem, there's pretty much only Cloudera, which is still selling Hadoop in its classical form factor. Right? But on the public cloud, a lot of facets of Hadoop have been now packaged and repackaged and sold as separate units for optimized for different workloads. Like if you want to do analytics, then there's a bunch of things that you could do from the Hadoop ecosystem, but it's not called Hadoop anymore on public cloud. Likewise, if you really want to do just SQL, then there's a bunch of things that's already packaged for you. If you really want to do only streaming, etc., etc. So all those options are now available. All right, so let's get into Hadoop itself. It's important you know what the technologies are because the concepts behind them are really important. So on top of HDFS, on Hadoop, there was created a management layer which was responsible for ensuring that the resources in the cluster were managed correctly, right? So that layer was called as YARN, or it stood for yet another resource negotiator. So why did this layer come about? The most important reason being the clusters which Hadoop ran were very large in size, and because they were large in size, and because they were a commodity hardware, you could have any number of things failing at any point in time. So one of the earliest, instances of observability actually came about with the introduction of YARN. Of course, it might not have been called observability at that time, but effectively, you need a way to manage a distributed set of machines and resources without having to physically go and log in, without having to physically check out, without having even virtually log into that machine and constantly keep checking whether something is available or not, etc. I mean manually checking it. So the automation around that was necessary for a few reasons. The first is, of course, what is the current resource availability? Second is, what is the resource utilization? Right? I might have a CPU that's fully utilized, in which case I don't have any more to allocate for any new jobs. The third being the health of the machine. So the machine is not reachable, obviously the resources are attached to it. are not available as well. The fourth being the distribution of workloads. So I have a machine, I have like a bunch of machines, I have resources associated with it. I need to run a job. The job needs to be distributed across all these machines in a certain way, and the distribution needs to be handled effectively so that everybody does not need to figure out what does it mean to do workload distribution. And the fifth being to provide a common layer through which multiple different tools can actually interact with each other, right? So I could have tools which are SQL based, like Hive as an example, right? I could have Spark, which is not SQL based at all, which has a very different backend. I could have streaming, which has a very different backend, etc. All of these need to coexist on the same machine, a set of machines. So in which case, how do they negotiate with each other on who's responsible for taking up the resources for a particular period of time? So what happens if somebody violates those principles? So all of those complexities, the kind of dirty work that's necessary for a bunch of players to work together, that's what Yarn was designed for. And because it was designed collaboratively by the community, every single library that you see out there on top of Hadoop eventually became compatible and became built on top of Yarn. So that's why Yarn is shown as a foundational layer. By the way, Yarn also manages the storage, right? Yarn also manages the disks that are there. So even though HDFS is shown as a service below Yarn, in effect, the HDFS service itself uses Yarn to effectively manage a bunch of storage disks that spread across the cluster. Okay, so Yarn, in fact, is so popular, so foundational. It's still very much in use, even in the public cloud. Right? They call it different names. It might be part of different types of packages, but Yarn is actually one of the most robust pieces of technology that came from the Hadoop ecosystem that's still in use today. All right. So on top of Yarn, you've got a bunch of different options based on what you want to do. We spoke about MapReduce. Not many people, in fact, I know very little usage of MapReduce nowadays. Almost everybody uses Spark, and we know the reasons why, right? And we'll reiterate those reasons again. We last looked at it in lecture 1. We'll look at it again later in this week's lectures. The second set of capabilities that came very early on is the need for SQL. In week 5 or week 6, I don't know which one, we will be spending some time on SQL. So, and I think some of you might have had exposure to SQL from before. We will talk specifically about SQL and big data at that time. But at the time when Hadoop came into picture, MapReduce was the only processing paradigm available. So you had to code in Java effectively. So that became very restrictive in terms of what the broader ecosystem was requiring. A lot of SQL developers exist in the world compared to, relatively speaking, the Java developers who could code on MapReduce. So one of the first packages that came, and in fact it came from Facebook, it was called as Hive. Hive was effectively a SQL lipstick layer on top of MapReduce as the backend. That's how it started. Over time, many different things happened. Hive became its own standalone package with a standalone backend. In fact, Hive itself comprises of 3 different pieces of technology. The first is the Hive SQL layer itself, which is called as HiveQL. That's Hive query language, which is the front end, which is the declarative programming syntax that developers could use. So it was like SQL, but not completely SQL. In fact, to be precise, it's not SQL standards, SQL 92 standard or ASCII SQL 96 standard or whatever that is. So it had its own nuances in the syntax. But that's the first, technology that it brought to the table. Along with it came what's called as the Hive Metastore. The Metastore is responsible for storing metadata about what tables exist in which part of the cluster, and what does that cluster, what does that table contain, what is the schema, etc. So, as it turns out, like Yarn, the Hive Metastore has survived to this day as a library, as a tool that was that's necessary, that's crucial for many public cloud big data packaging, right? So the Hive Metastore formed a crucial layer. Then the third tool that was technology that was part of the Hive library was the Hive backend, the query execution backend. That actually had so many different changes and options and redesigns and things like that. So today, if you see, you could find many legacy implementations of Hadoop still using Hive, especially in large enterprises. But it's quite likely that almost everybody uses some kind of a Hive metastore or the other, but they don't use Hive QL anymore, right? They've moved on to using other native SQL on Hadoop or native SQL on the cloud kind of options, because nowadays the Hive metastore as a layer has allowed a lot of different SQL front ends, meaning the programming syntax front ends to plug in without requiring to learn the Hive query language itself, right? And then the backend, of course, is going to be optimized based on the front end, based on the SQL that we provided the front end. So the front end programming syntax and the backend execution engine, the optimization engine, all of that has gone through multiple changes, but the Hive metastore is roughly the same. All right. Then what was also very popular at that time was the need for scripting in languages other than SQL, but not requiring Java, right? So remember, I said Python as a native support for Hadoop came a little later in terms of maturity. In fact, prior to Python becoming popular on Hadoop, the language that was of choice at Yahoo was this language called as Pig Latin, or Pig in short. It effectively was its own DSL, a domain-specific language, for writing scripts, which were kind of like SQL but more procedural, but didn't require the knowledge of Java backends, right? So it was more suited for scripting, for automation, for orchestration, and things like that. Even for some simple ETL jobs. We will take a look at ETL versus ELT in the next lecture, or the next week's lecture, that is. But yeah, for now, Pig Latin was one of the first scripts that came about. Nowadays, I don't think anybody uses Pig anymore. Same as last words, but yeah, I don't think it's that popular. Yeah, and the other library that became very popular back in the day when Hadoop was born, pretty much immediately, like within the first couple of years, was this NoSQL database called as HBase. Now, there's a lot of history here, which is itself worth digging into. So, we spoke a bit about it in one of the earlier lectures, but let's dive deeper here. So, NoSQL really stands for the fact that I don't want to use or don't want to be restricted by relational databases, RDBMSs. The reason for that philosophy was, back in the day, RDBMS for large-scale data processing only came from proprietary vendors like Oracle, Teradata, IBM, Microsoft, to a lesser degree. And those technologies were prohibitively expensive. So the tech landscape in the Silicon Valley and even beyond, they started to look at building their own alternatives. So they started to look at, for instance, obviously Hadoop for analytical processing, but then they started to observe this pattern that beyond a certain scale, I need to start having different backends for transactional processing compared to analytical processing. So we spoke a little bit about OLTP versus OLAP in the last week's lectures. That distinction became prominent in big data scale, whereby at some of the scale at which, for instance, Facebook or Twitter was operating back in the day, they realized that if you had to scale Oracle or Microsoft or IBM DB2, it would have required a phenomenally expensive infrastructure and licensing. So, whereas the need was very specific, which is very low latency, very high concurrency, small package, small payload size data writes and data reads and data updates, right? So that was a kind of CRUD pattern that emerged. So what the open source community around Hadoop did was to build a database layer which was extremely optimized exactly for that, and they built it on top of the Hadoop distributed file system, eventually building it with Yarn. But in the early days, even before Yarn came into the picture, HBase is there. And tongue-in-cheek, they called that entire class of technologies as NoSQL. So HBase, in fact, supported a pretty stiff programming interface. You had to use that to, put data in and retrieve data, and that's about it, right? You can't really use that for analytical processing, etc. It was very bad at doing things like joins. It was good at only single table writes, single table reads. Even the reads were not optimized for bulk data. It was optimized for single query lookup, single key lookups. So, in fact, HBase was quite restrictive in terms of flexibility, but it was very popular exactly for the reason because it was optimized for that workload of NoSQL. In fact, so much so, when Aadhaar was implemented in India, the first implementation was actually done on HBase at very large scale. So you can imagine crores and crores of transactions happening on a regular basis, and all of that being supported in latencies of less than a second. So there's a very good case studies available on that. All right, so that's HBase. HBase is still very popular, by the way, but it heralded an entire series of technologies all under the NoSQL umbrella. So much so that it's an entire class of technologies on the public cloud now. Like on Azure, you have something called as Cosmos. On AWS, you have something called as DynamoDB. On GCP, it has its own key value pair data store. I don't recollect the name right now, but yeah, so NoSQL is very popular. Now even before MapReduce came into picture in Hadoop, the first use case of Hadoop was actually for storing and indexing the entire World Wide Web. Yahoo was actually a search engine, and that was the main use case for which Hadoop was first built. And as a result, in fact, the first, Apache software that was open sourced from Yahoo under the Hadoop umbrella later on was Lucy and Solar. Together they form a very powerful pair. To this day, the Lucene backend is used in other technologies like Elasticsearch as well, I believe, but Solar is also very popular still for free-form natural language search, right, on top of textual data. So this was a library that came about. There was a specific library for coordinating multiple different types of workloads and making sure that they all ran in the right sequence, etc. So that scheduling was done by Uzi. Uzi is quite restrictive in hindsight, but yeah, back in the day, it was very popular and it was necessary. Because without Uzi, you wouldn't really know how to put Hive and MapReduce together, how MapReduce and HBase lookups together, etc. Right? So Uzi became necessary. Nowadays, there are other options, like some of the more popular ones came from Airbnb, which is called as Airflow. We might be taking a look at it later in the course. Machine learning, we're not going to spend too much time today on this, but yeah, back in the day, Mahout was one of the first machine learning libraries that were built on native MapReduce. In fact, one of the first uses of machine learning on Hadoop was building recommendation engines. So the world of Hadoop came from mainly the tech ecosystem, which is focused on ad optimizations and selling e-commerce products, right? So recommendation engines was the main use case for the most part. So Mahout was the library that was built to make available recommendation engines as algorithms out of the box. You could just use Mahout and the algorithm. You don't need to understand the internals, and you'll be up and running. So in fact, the world of data science, the way we understand it today, originated with Mahout as the library of choice for big data engineers, along with the Hadoop ecosystem. Later on, of course, Spark came about. Mahout itself was rewritten using the Spark backend. Then Spark MLOop took over. Nowadays, there's so many different machine learning libraries. I'm sure you all know it much better than I do now. Okay, so one of the most important backend technologies that was developed as part of Hadoop was something called a Zookeeper. In fact, Zookeeper is a very complex piece of theory behind it. For those interested, you can look it up. It's called the foundational theory there is called something called as Paxos, PAXOS. It's a protocol for ensuring that multiple different software which is running on multiple different machines can automatically agree on a particular state of data. When I say data, I mean metadata, really, control data. So to be able to agree is such a simple thing for us as humans, but what does it mean for a set of machines to agree on a state? So a state could be as simple as this is the size of the cluster, right? Like for instance, 10, I have 10 machines with me. Those 10 machines have 200 GB of memory available for me. They have 20 CPUs, etc. So it sounds like such a simple thing, but how do machines agree to it? It's a very, very fundamental problem. Because if you're not able to reason about that, then the entire edifice that's being built on top will start crumbling. Right? You can no longer reason about resources, because if you can't reason about that, you can't execute anything. You can't reason about failures. You can't reason about performance. All kinds of nasties happen, right? So Zookeeper was built as a consensus driving software or service. So every single critical piece of state that was maintained on top of Hadoop by these services, like Yarn, HDFS, MapReduce to an extent, some of the other technologies as well, all of that relied upon Zookeeper to ensure that the machines agreed with each other on the state, right? Zookeeper today, in fact, is still implemented as part of the Hadoop packaging, as part of public cloud packaging. In fact, there are other variants of the Paxos algorithm that got implemented as part of public cloud infrastructure. It was a very effective piece of technology. Ambari was the administration console for Hadoop. You didn't really encounter it nowadays because public cloud has its own administration console. So yeah, we'll skip this for now. The last item I want to spend a bit of time in, and we'll come back to this in a very serious way in one of the later week's lectures, is on streaming. Right? Streaming actually comprised of two different pieces of technology. The first that came about was something called as Storm. Apache Storm, was one of the first instances of open source, extremely large-scale complex event processing libraries. Complex event processing really is a specific technology category. It refers to being able to process streaming data and derive various data processing on top of the events. So we spoke about event as a paradigm in the previous week's lectures. Event sourcing was the specific way in which extraction from storage of CRUD data happens in the form of events, and that became like the basis for cloud native architectures. But even before cloud native was created, events were very common in certain industries, like manufacturing as an example, or machine data as an example, right? So in those cases, the events were being processed, actually even before the financial services, right? Yeah. So those events are getting processed or necessary to be processed in real time. So the CEP, complex event processing technologies, came about as a result. Before Storm was brought to the picture, the only option you had for doing this was, again, proprietary, very expensive technologies which had big infrastructure requirements. So Storm completely revolutionized the space. So Storm proved to the tech ecosystem that here's a technology that's open source, built on top of the Hadoop stack, that allowed you to do extremely large scale event processing, running into like millions of transactions per second with cost structures which were reasonable. After Storm, a lot of other technologies started to come into play for streaming, including Spark streaming. Nowadays, I don't think anybody uses Storm. It's not that popular anymore because it has a very specific set of constraints that it imposes on what you could use to program, as opposed to Spark streaming, which was a lot more flexible. And we'll talk about that later, right? Yeah, so Storm was born in that era, early days of Hadoop. One of the other popular technologies that was born in the early days of Hadoop, but became open sourced and supported by a bigger community in the later days of Hadoop, and now is such a popular piece of technology is Kafka, Apache Kafka. It serves the role of what's called as a message broker. So it is a very complementary piece of technology to the CEP class of technologies like Storm and Spark Streaming and Flink. Flink is another example in this space. Kafka as a message bus is remarkable in its characteristics, especially because it has a very simple design in the back end. And the people who designed it originally from LinkedIn, and then now they have their own company, the creators of it. But then nowadays everybody is contributing to it. Right? Kafka is a very, very popular open source technology. In a nutshell, Kafka became the de facto standard for exchanging messages across an enterprise in real time, if you needed data in real time. And because of its open source nature, a lot of libraries were built on top, and today the Kafka ecosystem is its own standalone ecosystem. A lot of associated technologies exist today. Yeah, but back in the day, Kafka was a message broker, plain and simple. You would pair it with a CEP technology like Storm or Spark Streaming, and you would be up and running and have extremely scalable real-time processing pipelines. Okay, so the last two technologies I want to mention were related to data being brought in and data being extracted out. So Scoop, as you can imagine from the name, it scoops data from structured data sources like RDBMSs like Oracle, Postgres, MySQL, etc. And it would bring data from there and dump it into HDFS. So we spoke about how data extraction from sources could be query-based, right? So Scoop was actually doing query-based extraction. So you could tell Scoop or query everything since the last time you were successful. So you could run Scoop on a daily basis and say, on a daily basis, pick up new data, and then it will pick up and bring it into HDFS. Flume, on the other hand, was meant for large-scale event data collection. So for instance, if you needed to collect log data from machines, from their operating system logs, kernel logs, and web server logs, and things like that. So Flume was really good at just tailing the log and collecting all those events and sending it over the network. In fact, the Flume architecture itself is like a very good example of a distributed agent-based architecture. You could deploy Flume agents in multiple places. It will just collect and bring it back in. So I mentioned about Elasticsearch. Elasticsearch is also an open source set of technologies which packages a bunch of things related to search. But one of the things it packages is something called as Logstash, and its companion technology called as Beats. So both of those are equally popular. So as Flume is, to deploy in multiple different places and build this distributed set of agents which can collect data on your behalf and keep feeding it back into a central system. By the way, Scoop can be also used to read data from Hadoop, especially using Hive. Okay, so with that, we've stopped this overview of Hadoop. In this next lecture, we'll start looking at Spark as well.